So you want your green sheet out because make sure I don't forget, we're going to add an equation in a little while. Not right away, but in a little while. Well, sorry, we're going to rewrite an equation so it looks differently and you'll have a bit of an aha moment. We'll get there. Power. Power is defined as the rate at which work is being done on an object. Lena, it's defined at how fast you're doing the work. If you're exercising and you're getting tired, it's not because you're doing work. It's because you're generating lots of power. For what it's worth, Zach, power is what causes tiredness, not work. Let me give you an example. If you walk up a flight of stairs and if you run up the flight of stairs, you've done the same amount of work. In fact, I can tell you how much work you did. It was mgh. You raised your mass times 9.8 times the height of the stairs. Which one is more tiring, walking a flight of stairs or running a flight of stairs? Why? You're doing the work faster. You're doing the work faster. Or the big stairs we have in the back corner of the field here, walking those, they're so shallow, they're almost awkward to walk, but you can walk them. They're designed that way to be so shallow because they know there's senior citizens or older people here that can't generate as much power. They can still make it up those stairs. They're very, very shallow. They could have made them steeper, would have been way, way harder to walk all those flights of stairs because why? You're having to do the work faster. You'll get more tired, generate more power. Can you, Mud, read to me this first sentence? Power is the? Stop. As soon as we say rate, you're dividing by time. Acceleration is the rate of velocity change, VF minus VF over time. Power is the rate at which you're doing work. Power, symbol capital P, not lowercase p. What's a lowercase p a symbol for? Momentum. Have I mentioned we're running out of? We are. Power, capital P, is work over time. Power is a scalar, no direction. What would the units be? Well, what are the units for work? What are the units for time? So power is measured in joules per second. Oh, got a latecomer. Pause for a second. So the units for power, joules per second, but power is such an important concept. We say a joule per second is something else. Power is measured in what? Power is measured in what? Power is measured in what? Okay. And this is problematic. This is good. But Danica, I'm not kidding that we don't have enough letters to go around, because what we now have then is this. Power, I'll come back to the screen, is work over time. That W is work, but you're going to get an answer in watts. That W is watts. And I'm sorry, we just don't have enough letters to go around. You'll have to just look at the context. Oh, and by the way, that's west if it's after an at symbol, although power is a scalar, so you don't have any direction, but we got west, watts, and work. W's the worst one. It's the one, N and W are used for three things. N is Newton's north, and some textbooks use N for normal force. You'll notice I always wrote Fn because I just didn't want to use N for that third thing. Okay. So 1 watt is 1 joule per second. If you are generating power at 1 watt, you're using up 1 joule of energy per second. Example 1, I like example 1, I like example 1, I like example 1. Example 1 is a nice question. An electric motor is used with a pulley and a rope to lift. Can everybody underline the word lift? This is a trigger word. A 650. Ooh, what are the units next to that 650? What is that? Which force? This here is mg. They apparently found the mass and multiplied it by 9.8 for me. Well, thank you very much. To a height of 12 meters, the job is done in a time of 10 seconds. Okay. Eric, what's this question want me to find? What is the? I guess the first thing that I would say is, well, I have my brand new power equation. Power is work over time. And Eric, I definitely got the time part. 10. Yes? Work. What's our equation for work? So Eric went one step further than I was expecting. He said mgh. It's force times distance. Let's write that first. But then yesterday we said it's the force that you lift with times distance. And we agreed yesterday, 2 days ago, we agreed that the force that you lift with, we did a quick free body diagram and we said, you know what? It's the same size as gravity. It is F lift, but I don't know F lift. Oh, but look, another force the same size as F lift. And so we said that when you're lifting, the work done by lifting is mgh. I agree. And if you go straight to that, I'm good with that. Eric, what's M? Oh, wait. No, Eric, what's mg? 650. H, 12. How many watts of power does this motor require in order to do this? This is an electric motor. What do you get? 780? Units, power is measured in watt? Okay. Direction, scalar, is none. Now, watts are the SI unit for power, but there is another unit that's still used to this day. I hate it. It's the horsepower. This is the imperial unit. 1 horsepower is almost exactly 750 watts. So the motor in this example, they would probably list it as a horsepower, maybe not. Electric motors, they usually do list in watts, but if it was a gasoline motor, they would list it in horsepower. How can I convert 780 watts to horsepower? Did I say convert? I guess we'll write down what they gave me, 780 watts. I want watts to cancel. Ashley, where's it going to go in my next fraction? What's going to go on top? What do they want me to end up in? Horsepower. What's the conversion factor? 1 horsepower is the same as 750 watts. Ashley, am I going to times by 750 or divide by 750? How do I know? It's on the bottom. That's that chain method that I taught you way back when in September. I still use it all the time in real life because I always know the conversion factor. I'm never sure, do I divide or do I times? And I've never bothered memorizing. I can figure it out in 1 second. So it's going to be 650 times 12 divided by 10, 708 divided by 750. And I get almost exactly 1 horsepower. 1.04, is that right? Is that right? Okay. Example 2. A 60-kilogram girl runs up a flight of stairs 3.32 meters high in 2.6 seconds. Okay. Lena, what does A want me to find? Power. I think I'm going to go power equals work over time. Did they give me a time? Okay. I can fill that in. How much work? Well, when you go up a flight of stairs, listen close, you're lifting your own body against gravity. Did I say lifting? It's going to be mgh. Those of you that are paying close attention to your formula sheet may notice that mgh appears but later because we're also going to describe it in a different manner. That's why I said you don't need to write this on your formula sheet. It's kind of snuck its way on there. Lena, what was the mass? G, H, 3.32, all over 2.6 seconds. What do you get? $750.8? Call it 751? Keep it on my calculator. Units, power is measured in watt. Just to put that in perspective, these stairs in the back corner over here, behind my room, They're right around 3.3 meters high. I've measured them, okay? So walking those stairs in 2.6 seconds, you're not sprinting them. You're not walking slowly and talking the whole time. That would be, I'm hustling but not running up the stairs. And 60 kilograms, all of you have a mass around 60 kilograms, plus or minus another. My point being, all of you can generate about 750 watts. In fact, most of you can probably generate about 1,000 watts. If 1 horsepower equals 750 watts, what's her power output in horsepower? Almost exactly what? 1 horsepower. All of you are capable of generating a horsepower for a reasonable amount of time, but then you'll get tired. Those of you that are in better shape can maintain that 1 horsepower of power for longer. Those of you that are in lousier shape get tired faster, have to stop and huff and puff. Okay? When you're trying to build your cardio system, those of you that are athletes, what you're really saying is, I'd like to be able to generate a higher power for a longer time without having to stop. Not do more work over a longer time, do more work quickly over a longer time. I got to go on a horsepower watt rant. Horsepower was originally defined by James Watt. James Watt, to me, is maybe the most overrated scientist out there, especially because the unit watts, you all know it because it's also used in electricity, electrical power. It's a fundamental unit that you run into all the time. And he didn't do much, in my opinion. Some people will say, well, didn't he invent the steam engine? If he had, that would be impressive. He improved the steam engine. But Danica, what he really was a good marketer. Back in the 1700s, he was trying to convince farmers to buy steam engines. And a farmer would say, what do I want a steam engine for? James Watt invented a unit called the horsepower. So he would say to the farmer, this steam engine is 3 horsepower. What does the farmer immediately think? This steam engine does the same amount of work as what? Totally made up unit. Has nothing to do with 3 horses. But it's sold. In fact, it was such a good marketing ploy. We still use the stupid unit today. We talk about engines in terms of horsepower, even though no one today knows how much work an average horse can do. It's garbage. There's my rant. You do not need to memorize that 1 horsepower is 750 watts. You do need to know that horsepower is a unit of power. I'm going to think that it's fairly easy for you to remember that horsepower is a unit of power. If I give you something in horsepower, I will always give you the conversion factor somewhere in the question. Like example 3, how long would it take a 10 horsepower motor to lift a 500 kilogram safe up to a window 30 meters above the ground? Ooh. Ange, what's this question asking me to find? Don't write this next bit down. Am I going to find time by going like that? Am I going to find time by going like that? Okay, point being, we're at a stage now where we have lots of approaches. So, how do you think I'm going to find time, Ange? Okay, power equals work over time. Let's get the T by itself then, shall we? Where is the T right now? On the... Blech. Okay, we don't do math with stuff on the bottom. Wait a minute. Dividing by T on the right is the same as doing what with the T on the left? So everybody, now that we've written that, by the way, I guess another equation for work is power times time. How would I get the T by itself? How will I move the P over? Okay. It's going to be work. Now, my trigger word, lift. What's the work done by lifting? I heard it. Not mg, that's a force. mgh, don't make that silly mistake. Okay, so it's going to be mgh on the top divided by 10? Why can't I put a 10 down here? Horsepower, we're going to have to do a conversion. Let's do that off in the margin. How about right over here? I'm going to say 10 horsepower. Zach, I want horsepower to cancel. Where's it going to go in my conversion fraction? Yeah. What am I going to put on the top? Sorry, I didn't say that right. What am I going to put on the top? What am I going to put on the top? What am I going to put on the top? Help me out, folks. Really? What's my conversion factor? I guess 750 watts is 1 horsepower. And here's my question then, Zach. Am I going to go 10 times 750 or 10 divided by 750? And I'm so lazy, I'm just going to put 10 times 700. You know what? I can do that in my head. 10 times 750? Yeah. Okay, my units are all good now. I checked the rest. It's all meters and kilograms, and there's no grams, there's no centimeters. So it's going to be M G H How long will it take? Do you get 19.6 units? Someone said watts, really? Time, seconds. What if you need the job done faster? You have to get a bigger motor. It's impossible to do the job faster. Now, this is kind of a silly example, but how many of you have seen those massive building cranes, the ones with the huge scaffold that they also raise as the skyscraper goes higher? Okay, you can actually fairly accurately calculate based on the power of those cranes and the mass of the material you need to lift up. You can calculate how long it's going to take to build the building. It's a bit more complicated because the crane's heights are changing. It's a bit of a calculus question, but they do that. This is one of the ways that they predict, okay, how long is it going to take us to build this skyscraper? Bare minimum, we can calculate how long it's going to take us to get the materials to the right heights. What if you need to go faster? Get a bigger crane or get a second crane, otherwise you're stuck. Power can also be measured in kilowatts, 1,000 watts, or megawatts. Megawatts, you'll often hear them talking about when they're talking about a hydroelectric dam generator or something to that effect. Kilowatts, you'll often hear them talking about how much energy a house uses, how much power a house uses or something like that. Turn the page. The power of a light bulb is the amount of electrical energy that it consumes in 1 second. A 40-watt bulb, for example, uses 40 joules of energy per second. A 60-watt bulb uses 60 joules of energy per second. A 100-watt bulb uses 100 joules of energy per second. Suppose we have a light bulb that consumes 40 joules of energy in 70 seconds. What's its power? Dan, how do I find power? Good. And I'm glad you looked at your green sheet. You're training your eyes to look in the right location. What are the units for work, Dan? Starts with letter J. Joules. Now, ready? This is a bit of a spoiler, but you're going to learn after Christmas. Energy is the ability to do work. And so energy is also measured in joules. Work and energy are not technically interchangeable, but we are going to interchange them and be sloppy because I'm going to give you careful questions where we can interchange them. So how many joules of work is this light bulb doing in this question? You got it. Keep reading. Yes. Over how much time? Yep. What's the power rating of this light bulb? I think I do that in my head. Is it 60? Is it? Yeah. The 60-watt bulb. A microwave is rated at 1.2, what would kW be? Kilowatts. How many watts is 1.2 kilowatts? How could I do the conversion quickly? What about 1,000? What will I do with the 1,000? Multiply. What's 1.2 times 1,000? This is 1,200 watts. It's running for 6 minutes. 6 what? Nice try, Duick. 6 minutes. How many seconds? How do you get that? Okay, and you can do the full conversion fraction chain, but I'm also hoping we've come far enough that you've got some shortcuts that you've just picked up along the way. Kilo, kilograms, kilowatts, kilometers is a nice one. Centi is a nice shortcut to have, and I think going from minutes to seconds or hours to seconds, if you can do that without building a full fraction chain, I think that's good. So 300. Okay. Nick, what's example 5 asking me to find? How many what? How many what? You're right. Say it again loud and proud. How many what? Joules. They gave me power. You know what? They gave me time. I'm going to write this down. Nick, which of those 3, power, work, time, is measured in joules? Is time measured in joules? Okay, so ain't that. Power is measured in watt? Power is measured in watt? So is power measured in joules? What's measured in joules? It's got to be work. Let's get the W by itself. Nick, what's the T doing to the W? So another way to find work, which is energy, is power times time. How much power? 1,200. How much time? 360. Your parents, I'm assuming none of you pay your own electric bills, your parents' electric bill, they get charged for how much energy they use. Using a microwave for how long? 6 minutes, not very long, is almost 500,000 joules of energy. Typically, a house would use tens of millions of joules of energy per month, or hundreds of millions of joules of energy per month. And that would terrify your parents if they got their energy bill with hundreds of millions or even billions of joules. And so, although science, the unit of energy is the joule, by the way, let's write this down, 432,000 joules. Your parents don't get billed in joules, they get billed in, oh, don't want to cross it out, kilowatt hours. Now this is a bit tricky because kilowatt hours looks like power, watts, or hours, time. Wait a minute. No. It's power times time. See it? Power times time. Kilowatt times hour. What's power times time a measure of? Energy. Work. So your parents get charged on their bill in kilowatt hours. 1 kilowatt hour is 3.6 times 10 to the 6th joules. So how many kilowatt hours does this thing use? Well, let's write down what they gave me. Keegan, I want joules to cancel. Where's it going to go in my conversion fraction? Yep. And this new unit, kilowatt hours, lowercase k, capital W, lowercase h. And what's the conversion factor? Apparently 1 kilowatt hour is 3.6 times 10 to the 6th. Am I going to times by 3.6 times 10 to the 6th or divide? How do you know? Okay, so I've got this number sitting on my calculator divided by bracket 3.6, scientific notation button 6. about 0.12 of a kilowatt hour. That's a much more manageable number for most people to wrap their brain around. I'm going to give you a few questions in the homework in kilowatt hours. I don't think I'm going to put a test question in kilowatt hours because I prefer to use the SI units, but you should know what they are because all of you someday will pay an electric bill. Kilowatt hours is a measure of energy, not power. I have a photo here that I call bad physics. This is something I saw on a bus station. It said burn calories, not kilowatts. This says burn energy, not power. The units don't match. Could say burn calories, not kilowatt hours. Burn energy, not energy. In other words, burn human energy, food energy, not the energy you're getting from the power lines. This just units don't match. Yeah. Bad physics. Example 6. I like example 6, I like example 6, I like example 6. It's a nice question. Ooh. Brandon, what's example 6 want me to find? Am I going to go VF minus VI over A? How am I going to find, which approach am I going to use? What has time in it and some of the information? Give me an equation, kiddo. Give me an approach. Oh, you're saying I'm going to find time using power. Okay. Get the T by itself. How would I get the T by itself, Brandon? And? So T equals, I guess, what? Work over power. What are the units for work? Which means it's also energy. So I guess it's going to be 40,000 divided by 800. And I get 50 units seconds. So this is how they can calculate how long you need to, the instructions on your microwave package or whatever, this is how they calculate how long you put it in the microwave for. Actually, large microwaves are usually rated at 1,200 watts. Small microwaves are usually rated at around 800 watts. How long would it take to cook this in a large microwave? Well, I guess time is work over power. It's still 40,000 joules of work divided by 1,200. That's messy, Mr. Dewick. How long in a large microwave? 33.3. This is why you may have noticed, what does it always say on the back of the instructions if you're microwaving something? Microwave oven times may. Always says that. Because they don't know the wattage of your microwave. So you know what they probably do? Take an average. Yeah. Turn the page. Or next page over. There is a special version of the power equation if we are moving at a constant speed. So what's power? Can everybody in this box write power equals work over time? And then, Karen, what's work? What's our equation for work? Can you put an equal sign, force times distance over time? And then what I'd like you to do, circle those two. Taryn, what do I measure distance in? What are the units? What do I measure time in? What is meters per second? A measure of. I've seen that before. Technically, since we're in scalarville, not velocity, but speed. Another version of power is this one. Power equals force times speed. I'd like you to add that to your green sheet right next to where you have the power equation. You can do it in one of two ways. Look up. You right now have power equals work over time. You can just put an equal sign and say, hey, it's also force times speed. Or if you're someone who has to have it separate, you can wedge it in beside there somewhere, or underneath, or above, or something. Power is work over time, but because work is force times distance, power must be force times a constant speed. Okay? Is that all right? Y'all added it? Let me give you an example. Emma, what does example 7a want me to find? How much? Okay, look up. This is how my brain is going to work. First thing that I would do is I would go, well, power is work over time. Write that down. Then I would read the question carefully. Do you see a time in seconds anywhere? Do you see work in joules anywhere? And I would say, well, it's also force times speed. Ah! Do you see a force? Do you see a speed? Okay. Now, if I didn't see a force and a speed, then I would say, well, maybe I can figure out the work, or maybe I can figure out the time, or maybe I'll have to do, this will be like a multi-step question. But for now, this is going to be a straight plug and chug. It's going to be 32 times 12, which is what? Emma? 384? You're generating 384 watts of power. Okay. If you want to go faster, will that require more power or less power? Be very obvious. Why? Because you're multiplying by the V, you're not dividing by the V. Yes? So, and part C, Captain Obvious, but does pedaling faster make you more tired or less tired? Why? You're generating more power, and power is tiredness. And I know all of you have clued in, oh, if I pedal faster, I get more tired. Oh, by the way, work is what times what? Your gear ratios on your car, on your bikes, those are messing around with the distance in order to require you to apply either a bigger force or a smaller force. So the smaller gears, like the higher gears on your bike that are harder to pedal, increase the force at the expense of reducing the distance. You can get more work. Okay. Ooh. How could a cyclist go faster but use less power? Well, we said power equals force times speed. What force is that? Well, it's your pedal force, I think. But we have a constant force to overcome air resistance. How can I go faster but use less power? Tuck. More aerodynamic, less air resistance. Now you'll have an unbalanced force. Go faster. And I've talked about this before, but yeah, now we're explaining the whole Tour de France, why every cyclist adopts the same pose. The professionals, they've all practiced in wind tunnels. In fact, they've memorized specifically the best pose for their own body, because it would depend on how long their legs were, what their height was, how bulky their back is. They've all memorized their pose, and that's what they freeze into. They'll all be fairly similar, but they'll all tweak it fairly slightly. All right, what's your homework? Number 1. Number 2. You know what? I'll let you skip number 3. Ha 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 ha. Okay. 4 is good. You can skip 5. 6 is good. 7 is good. 8 is good. 9 is good. And 10 is good. I haven't taught you how to do B yet. B asks, how efficient is this elevator? Guess what our next topic is going to be after the break? Efficiency.